we notice that there are D's everywhere. Each term has a D, but let's say you didn't notice it, then you would take those D's, the ones that just have a single D, bring them over to one side. Actually, I'm just going to factor them out together. Minus. Okay, so this one, all brought over to the other side. There's a D and a D squared here. So it becomes 1/2 KD equals mu K mg cosine theta minus UG sine theta minus K xi. Therefore, D is negative. It's interesting. Let me just make sure I didn't leave it on some 9 aside somewhere. If that's minus, that's plus, x plus d, that's right. And minus pkn, minus that, and that. Oh, that's fine. So this gives us a d that is minus what value? Oops, I know one thing, something here. Actually, there's one thing here I have to change. I don't need those here. If I do it this method, no absolute values. The reason I want the absolute values because xi in this case is minus, what did we say, 0.3. And it's minus because it's compressed. It's on the other side of the equilibrium position. So x initial is minus 0.3. What do you get as a value? You're given your mu k, you're given your m, you're given your g, you know your theta. What do you get? So what do you guys get?
Now, hopefully I didn't goof it up, but I got negative 0.45 meters.
Did you put x initial is minus 0.3?
Okay. Yeah, no, I didn't. No, I put 0.2, but I didn't put the negative. Sorry.
Okay. I do think we have one other maybe mistake here. Yes. What is our mistake here? The minus sign here. Again, cheapers. We said delta H was negative, going down. Ay, ay, ay. Minus sign over there, guys. Minus sign over here.
Yeah, I don't know. I can't get it myself. Not sure why.
So the D that you get with this calculation is going to be 0.458
Yeah.
meters. Now, this tells us that the mass went past equilibrium. So, and now you have to do the same calculation. But set this time, this term here, you remove it because that term only pops in when it does not go past the equivalent position. So the way this problem is phrased from your textbook, because they left it open-ended, you would have to verify that it goes past equilibrium position. This D is greater than 0.3. Okay, so it's gone past equilibrium position, which means now you have to recalculate it because you've calculated it with this correction. In other words, you've calculated it using this correction here, that your X final is not just X equilibrium, that your X final is equal to X initial plus D. So now that we know that it goes past X equilibrium, the delta US is simply going to be, this is 0 minus 1/2 K X initial squared. So our scenario is this one here, which means our
Miss, I
X.
have a question.
Yeah.
It's about the problem, but not related directly to the problem. If, let's say, you were to give us this exact question on an exam,
I would
or a
tell
test.
you that it's gone past equilibrium or not.
Okay, perfect.
Like you would have the information, you would know where the final position is.
Okay, because like let's say we just had like this actual.
If you don't
exact
have it, just
question.
like in real life, if you have something like this, you have to test it because
Like,
you won't know.
How many points would be lost considering? Well, now we know.
But you're not.
Obviously,
I'm saying I wouldn't give you something like this on your test, but I'm saying in real life, if you have
Okay.
this in your real life, you have to test it because there's nobody's going to tell you it did or didn't.
Okay. Perfect.
So you have to test whether or not friction is strong enough to stop it before equilibrium, or it's weak enough that it allows it to go past equilibrium. And so in this case, since this is greater than 0.3, it went past equilibrium, which means that your delta US is going to be US final minus US initial, which is going to be 1/2 KX final squared minus 1/2 KX initial squared. Your KX final is 0 because it's at the equilibrium position. This is what's left, which is 1/2 KX initial squared. So in other words, this part here gets removed and you just have this instead. You'll just have instead 1/2 KX initial squared. And you will solve for D. So in this actual problem, knowing, so let's say, get rid of this. This simply becomes 1/2 KX initial squared minus specifically. And so this whole thing just becomes a simple minus 1/2 KX initial squared. And you're just solving for D. So typically, you would be told, and you would not be given at this level a hard problem. But because you weren't told in the problem, you had no idea whether or not which scenario was present. Now, all of this you could ignore, which means that you have from equation 1, your delta K is 0, your delta UG, which was mgd sine theta, and our friction totals became G. We're looking for D. So bring all the D's over. Factor out the D. And D is equal to. So now if you plug in your numbers for this, what did you get? You get 0.64 meters. So this problem, to be clear, let's say for your level, should be phrased as follows. Where's the question? How far down this? At least for this. Oh, I can't. So that way, you know that it loses contact with the spring, which means it's past the equilibrium position, and the problem would be clear. Any questions? Okay, guys. Next and last problem. Actually, before it won't be a problem, I'm going to stop sharing. I'm going to go over some of the notes instead. This is why I said it was important that you get the first part of the material covered well, because everything that we do from now on pretty much refers to bits and parts of what we've already covered. I'm just going to go over this last part in terms of the notes. Whenever you have energy involved and energy is being transferred from one object to another or from one location to another, or let's say work is being done by some force on an object, and remember work is the transfer of energy, the rate at which work is done is called the power. So let's say you have a book here or another box here. So you have two boxes. This is the ground. Distance here is h, distance here is h. Same exact box, same exact height. In one case, this first case, you lift the box from the ground up a height h in a time of, let's say, 5 minutes. You lift this, well, let's not exaggerate. 1 minute. You lift the same box a height of h, and let's say you do this in 30 seconds. The amount of work done by the applied force, let's say you apply the same amount of force, you apply a 100 Newton force in both cases to lift this box. The work done by this 100 Newton force in both cases is the same. You have 100 Newton force. The object is displaced at distance h, displacement h. In both cases, the work done is exactly the same. 100 newtons, let's say h is 1 meters. That's 1,000 Newton meters in both cases. What is different is the amount of time it takes to do that work, the amount of time it takes to lift that box. In one case, it takes 1 minute. In another case, it takes 30 seconds. So the power involved in the first case is less than the power involved in the second case. So power is a measure of the amount of energy transferred per unit time. And we can calculate it as work per unit energy, but we know that work is force and displacement. And therefore, displacement over time is just v speed or velocity. But if we are now looking in terms of rotational motion, the work is torque times the angular displacement. So instead of force torque, instead of linear displacement, angular displacement over time. And delta theta over delta t is omega. So it can also be calculated using the torque and the angular speed of the object involved. Now, units of power are the watt. 1 watt is 1 joule per second. A common non-SI unit, the US unit of horsepower, 1 horsepower is 746 watts or 550 foot-pounds per second. A kilowatt hour, which is what Hydro-Quebec charges you for, is not a unit of power. It's actually a unit of energy. So Hydro-Quebec actually charges you for how much energy you use, not how much power you use. And so your kilowatt hour is energy, because we said power is work over time. Power times, if you cross multiply, times time is equal to the work. Power is in watts, time is in seconds, or in this case, hours. So kilowatts times an hour is equal to work, which is equal to energy. Specifically, 1 kilowatt hour is equal to 3.6 megajoules. Now, when you have some sort of machine or mechanical system that does work, so in other words, you're putting in a certain amount of energy, you're putting in a certain amount of force, and it outputs a certain amount of force or a certain amount of energy, no machine is 100% efficient. So whatever you put in is not what you're going to get out at the other end. So if you put in 100 joules of energy into the system, you're not going to get 100 joules of energy out of the system, because there's always some loss due to heat within the mechanical system, due to friction within the mechanical system. Nothing is perfect. So the machine is never what we call 100% efficient. So efficiency is measured as output over input times 100%. So the useful energy, which is the output, over the total energy consumed, what you put in, times 100%. I think we'll leave this problem for next class. Now, next class, which is Friday, might be an asynchronous class, meaning it will not be live online. I will assign something for you to maybe watch and do and hand it at a specific time, not necessarily during class time, but during the day perhaps, or maybe by next class, by the following class Monday. But chances are, if this Friday's class is going to be asynchronous, not live online. Okay, I will post instructions by then. Any questions?
Is the efficiency on the formula sheet, or can we add it?
You could add it. I don't think it's on the formula sheet. I'm not sure, but I don't think it is.
Okay, I don't see it, so I'll add it.
Yep. Any questions on anything I said so far? Go over those problems that are in the notes. Look at the two different methods. I tried to do the alternate method in class. You have the other method in the notes. There are suggested problems that have been posted. Do those as well. Friday's class will pertain to those type of problems and to power. So look over the power examples as well that are in the notes. If that's it, then we'll call it a day. And if I don't see you Friday, I will see you the following Monday. But there will be an asynchronous class. It's not no class. It just probably won't be synchronous online live.
Okay, thank you, Miss.
Okay, you're welcome.
Right,
Do
thank
we
you.
Have a good
have
week.
any labs or quizzes coming up soon, or is it just the final exam? That's left?
That's true. The Friday's class could be a lab type activity. So it will be probably a mix of lab and activity. It's
Okay, so
energy
it's going to
related.
be-
Yeah,
okay,
it's
and
energy
that's going to
related.
be for the asynchronous class.
Yeah.
Okay,
Yeah.
so for the asynchronous class, you're going to post on Moodle with the
I'm gonna-
instructions, and we just do it on our own.
On
or are we gonna be
Moodle
in
or
Teams?
Leia. You could
Okay.
do Teams. If I ended up doing the lab activity version, it'll be Teams. Otherwise, it'll be your own.
Okay.
I mean, you
Perfect.
can always work together. It's not like
Okay.
okay.
And for quizzes, do we have any coming up, or is it just the
Next
final
week.
exam now that we have?
No, you
Okay,
have
perfect.
you have a quiz coming up on energy, and you might have one more quiz depending on the timing on momentum.
Okay, perfect. And then
Okay.
after moments and impulses, we're done.
Oh,
for the
that's what I
semester,
meant by
basically.
momentum and impulse. That's,
Oh, yeah.
yeah.
Okay, perfect.
So this Friday is asynchronous lab, or is that not official?
It probably will have a lab activity, yeah, plus
Okay.
some
Okay, thanks, Miss.
a joint thing, yeah. You're welcome, Eilish.
Bye bye.
Bye.
Have a good week, man.